I'm going to talk about a couple of interesting experiences in observing strange clouds on Jupiter. The first event happened in 2009 through about 2011. I have never seen Jupiter like that before or since. Let's go to the first slide. Uh, to start off with, I'm going to go over some nomenclature about the clouds and other structures on Jupiter. First of all, this is a picture with south up, which is the way I usually present it. The south polar region is this region up here. And as you go down the planet towards the north, we see the south temperate zone, the south temperate belt, which is the dark band, the south tropical zone, the light band there, the south equatorial belt, which will star in my first event, the equatorial zone, the north equatorial belt, the north tropical zone, the north temperate belt, and the north polar region. There's several other thinner belts in between the polar regions and the temperate belts, but they sort of come and go. Uh, Now, we also have white ovals, which are anticyclonic features, whereas their circulation in the opposite hemispheres are opposite what they are on the Earth. In other words, in the northern hemisphere, instead of being counterclockwise like they are on the Earth, they're counterclockwise, and the reverse in the southern hemisphere. Uh, the the Great Red Spot is one of these anticyclonic storms, but it's just the biggest one that we have, about 300 years old. And of course, there's the South Tropical Disturbance. You can look at that as the wake of the Great Red Spot moving at a different velocity from the clouds in the South Equatorial Belt. And there's the satellite Io and Io's shadow. Barges are these features here. They're dark cyclonic storms, not anticyclonic storms, and they generally occur on the northern edges of the north equatorial belt or up in the south equatorial belt sometimes. The dark belts are the lowest clouds. They're about 1 to 2 atmospheres. They're composed of ammonium hydrosulfide. The light zones are higher than the belts and they have upwelling circulation. And they're a much lower pressure. They're made from ammonia ice crystals. The great red spot and the white ovals are anticyclonic storms that are higher than the zones, high pressure regions, and when they get big, they turn red, like the great red spot is. The barges are cyclonic storms, higher than the zones, extend deep into the atmosphere. They're low pressure regions. Here is a schematic of the structure of these cloud bands. You can see the belts are lower and darker. The zones are higher and lighter in color because they're made out of ammonia ice crystals. Okay, here is the event that happened back in the 2009, 2011 region. This is an image that was taken late in 2009, and it's essentially Jupiter's normal appearance. However, as 2009 developed, some haze appeared over the whole planet and gradually spread to the south until the south equatorial belt was completely obscured clear up to this north tropical zone, and only the great red spot was left sticking up through these clouds. They were clouds of ammonia ice crystals. And this picture here is one of my first pictures that I took with the Sharfman medial refractor, which is my favorite planetary instrument today. I had been building during this period here and not doing any observing. Well, as we went into 2010 and 2011, this overcast covering up both the south south tropical zone and the belt and the zone above it persisted throughout most of 2010. But in November of 2010, these little band of cyclonic storms appeared and gradually spread around the planet. And during the rest of 2010 and early into 2011, the overcast dispersed, and when Jupiter was again visible after it went around the back of the sun, it was essentially back to a normal appearance again. I have never seen or heard about this happening before, and it hasn't happened since. But it was essentially ammonia coming up through the equatorial zone, spreading out and freezing over the entire southern hemisphere. And very interesting to photograph. Now, this is a recent phenomenon. It happened last month. I'm sorry, what?
Please be careful about the laser.
Okay, sorry about that. Turn it off for a while. On April 10th of this year, I saw something peculiar on the equatorial zone of Jupiter. This is a blown up image of it. I want you to look at this strange formation and this one. This one didn't last, but this one was with me for quite a while. A very peculiar shape. It looked first like maybe several of the white ovals were just near one another. They would either merge or drift away from each other. However, on April 13th, this was the image that I got. You can see that at least the smaller one has intensified. You can see it's clearly a high altitude formation. It's above both the equatorial zone and the the equatorial zone and the north equatorial belt. And it's overlapping into the dark region. Again, here's the enlargement of it. There is a small round section on either side of a large central region. And the strange thing is that the shape persisted for 7 revolutions of Jupiter. Most of the clouds on Jupiter that you see are transient features unless they have cyclonic or anticyclonic circulation to stabilize them and keep them. I mean, the Great Red Spot has been going for maybe 300 years. And some of the white ovals last almost as long. Well, here is a blow up of the thing, and you can see that if they were white ovals with the anticyclonic circulation, with these opposing circulations, they would probably tear each other apart. And in fact, when white ovals come together, they generally merge to form a larger oval. That's how oval BA formed. That was the one that was called Red Spot Junior, and it's still going around Jupiter now. It's lost most of its red color. It's sort of a very pale pink now. But what you would expect if that were the case was that it would immediately degrade into a larger spot. That did not happen. Well, I was wondering if I were imagining things, or was I seeing an aberration in my telescope? But one revolution later, some observers in Japan, Kunihiko Suzuki in Yokohama, he observed it too. Right there it is. There's an enlargement of it. And just a few minutes later, Yasuaki Saito, he also observed it. He didn't have as good a seeing, but it's there. So here is something that survived 8 revolutions about Jupiter and kept its form, which is hard to understand. Uh, I mean, they don't, you know what happens to a cumulus cloud on the Earth? It breaks up, changes shape all the time. But so I still don't know what this is. Uh, one possibility, I don't know if this has ever been discovered before, if you were to have 3 clouds that had one was counterclockwise and 2 of them were clockwise, the circulations might reinforce one another and might allow it to persist. But I'm going to float this up to Alpo and maybe the folks at the British Astronomical Association to see if they have an explanation for this. If this is not there, I mean, I might have to conclude that there are rodents on Jupiter. And now for something completely different. As you know, I have been observing the recurrent nova T Corona Borealis since 2024, when it was expected to blow up because they saw a decrease in the brightness that preceded the 1946 eruption, and everybody was ready for it to blow up. Well, it didn't blow up, and uh, I made about over 200 observations of it during 2024 and 2025, and I've just now started my 2026 campaign. These bars here are what the other people at the AAVSO have been observing. Here's my first point back in March, and the 3 points that I've gotten in May so far. And you can see that my measures line up with the other folks very well. This is a check star that it's of known magnitude, and I just use my calibration on that to make sure that I'm honest. Now, there is another prediction coming. I'll get into what that was in a minute, but it's supposed to happen sometime in June. This is when the white dwarf reaches the same point in its orbit that happened in the last eruption. Now, of course, it does this every 228 days, but they figure that once the layer of hydrogen builds up in the accretion disk, it gets to this critical part of the orbit, and then it blows up. Well, this was a prediction from a French astrophysicist named Schneider, and here's how he made this prediction. He proposed that TCRB's thermonuclear runaways are tied directly to the alignment of the red giant and the white dwarf. He calculated that eruptions occur roughly every 128 orbital cycles, with each orbit lasting about 228 days. Well, the first predictions at March in 225 and November 225, they failed. It didn't blow up then either, and I observed it through that. The next statistical orbital correlation windows are June 25th, 2026 and February 8th, 2027. Well, I'll be looking. I'm not particularly optimistic, and here's the reason why. There's about 11 of these things in the Milky Way galaxy. Here they are. T Corona Borealis is at the top. That one at the very bottom is possible. We're not sure that it really is a recurrent nova. But if you look at these things, they're spread out, and if you count the years between eruptions, here we have T Corona Borealis, 79 years between 2 of them, 80 years between the other 2, and everybody assumed, hey, this thing is like a clock. It's going to happen in 2024. It didn't, okay? Well, look at all these other ones. There's nothing particularly special about this one. They all are a white dwarf orbiting a red giant, and they all periodically have a thermonuclear explosion in the accretion disk of the white dwarf. But look at these these periods. I mean, for example, RSO Fiucci that I observed back in 2021, 9 years, 26 years, 12 years, 13, 9. I mean, there's no regularity to that. It sort of blows up when it feels like it, you know? Well, I averaged out these periods and I calculated the standard deviation, the error in that estimate. And it looks like that there is an error of plus or minus 10 years in all of these things. So I think it's just a statistical roll of the dice that we happen to have two periods for T Corona Borealis that were about the same. But who knows when it's going to happen again. The light blue, is when my prediction for the next one is going to be 225 plus or minus 10 years. Well, minus didn't happen, but I figured that somewhere before 2035, it probably is going to blow up. But I'm not counting on it blowing up tomorrow or June 25th when the Frenchman said it's going to. So anyhow, I quote a famous philosopher, Yogi Berra. It's tough to make predictions, especially about the future.
Hi, everyone. Okay, so back in September, Donna and I went to Stan Honda's Milky Way astrophotography workshop. That was held from September 19th to the 21st, from Friday through Sunday. This was to learn how to take images of the Milky Way just using a camera and a tripod. So this was our preparation. We needed to have a sturdy tripod, a camera, good camera, a wide-angle lens or a zoom lens, and these were the cameras that we had. And we also had a remote shutter, and some of the essentials like batteries, bag for gear, extra layers for clothing layers, etc. And we arrived at Estes Park, which is the town. This was in Colorado, and we arrived at Estes Park outside the Rocky Mountain National Park the day before on Thursday, and I'm making a point of saying that because, well, not only did we have elk there, but it was also beautiful, clear blue sky that day and into the evening. And of course, this was some of our, other friends that joined us when we were staying at this lodge. It was big elk country. We did have some time in the daytime to walk around the town, and I was able to do a little bit of long exposure imaging, so we left this picture in there. This is the stream that, the Fall River, I should say, that runs through the town of Estes Park. Okay, so the way the workshop ran, Stan Honda, a lot of you probably know him. He's a photojournalist and he does a lot of night sky photography. I think he's 120 NASA APODs. And he does most of his photography in New York City, believe it or not, night sky. So you can do night sky photography anywhere. The way the workshop ran, it was Friday through Sunday. In the afternoon, we spent at the Conservancy Center. And the first day, he did such a great job at preparing us what we needed to know to go into the field. Now, I have a DSLR camera, I always have it, and I take a million vacation photographs with it. So I thought, how hard can this be? But I just put it on auto and pretty much go out there, and I take 1,000 snapshots, and hopefully I get 5 good pictures out of it. So the whole concept, and you'd think doing AP, like at night, I would know something, but those objects just sit there, and I'm on my deck, and I don't have to move equipment around or walk around too much in the dark. So there's a big difference. So he talked a lot about planning. If you're going to go out in a national park, there's a lot of hazards around and lakes and moose and other things. And
you need to know ahead of time where Milky Way is. I mean, that sounds obvious, but it's not. When you go out there, you want to put your tripod down, set it up. You want to compose your photograph ahead of time. Look at the background, the foreground, find interesting objects, and get set up. Because when it gets dark out there, it gets really dark out there, and you don't want to be moving your equipment if you don't have to. He suggested using things like Stellarium, Aquarius, so that you know where the Milky Way is going to rise. Basic Stan is a minimalist. He said he doesn't ever crop his photos. You want to capture everything that you can, and so you really need to compose ahead of time. He went through the basic camera settings that we need. Again, I normally have my camera on auto. You really have to learn your camera because at night you need to change your settings as light dims. So Mary mentioned that you want to go in there with the widest lens possible. You want to capture the biggest part of the Milky Way you can, most of the landscape. So you need a wide lens and something fast because you're going to be photographing at night. And you don't want to go past a 15-second exposure or you're starting to get star trails, which you can pull a feature, but it's better not to have them in a Milky Way photo. So at twilight, you might be able to set your camera at an ISO 200, a little faster number of seconds you take a photo at. But at night, if you're in a bright city, you have to up the ISO to maybe 1600. If you're in a national park with no moon, you can go up to 6400. For those of you that do this kind of photography, that seems very high. A lot of times we get very grainy photos, but those you can process out. If you don't capture enough light, you can't bring back what you don't have in processing, so that's important. Because you're going to have to photograph it maybe up to 15 seconds or more, you need to have a wire shutter release or an intervalometer, because if you touch that camera to start it, taking the picture, it's going to shake and you're going to blow your picture. And the other thing is, if you're taking night photography, you have these nice live views on your camera, but they're all lit up. So things look great in there and they look really bright. But Stan was very careful to say, use the histogram in your camera, learn how to use that, because you can't trust that lit up little live view that you have to help you with picture taking. So he stressed that. Focus, something I never really thought about. I think about it for night sky, but with my DSLR, you hit autofocus and it just focuses. Well, try to do that at night when there's just tiny little stars out there. Your camera will try to focus and try to focus, and it just doesn't find a focus point. So you need to do a couple things. A lot of photographers focus during the day, believe it or not, at something really far away, and they literally take high-tech. They take their camera, their focus ring, so it doesn't move, and then focus at night. I'm terrible at that. I always end up touching the ring somehow. The other thing is, if you're at night, you really have to find something, the brightest star you can. If the moon's out, that's great, or somebody with a light on in the distance. But it can be difficult. If you have a mirrorless camera, it's much easier. There's a lot of focus assist. My camera is mirrorless, and the stars will actually turn red once they're in focus, so that's very helpful. But the big thing is practice, practice. All these things that are so easy during the day just seem so much harder at night when you're out there. So this was us setting up. That's me in the front, and you can see Mary. We were by a lake right in the middle of Rocky Mountain National Park, and we were going to be there till 11 or so at night. The one thing you always have to be prepared for is wildlife. And when this moose showed up in the lake as we were setting up, Stan takes out this lens that looked bigger than my telescope, put it on his camera because he's prepared for everything. That's a sign of a real photographer. We were with the guide. The guide told us, don't worry about the moose. They are kind of dangerous. They do run fast, so don't try to outrun it. But they really are very clumsy, and they can't see well, so hide behind a tree. Fortunately, we didn't have to see if that would work. So just to recap some field challenges, got to watch out for the moose. You got to be really careful with the tripod. It gets dark, there's rocks, there's roots, and it's so easy to find out that you put the Milky Way behind the tree and now you have to move everything in the dark. So again, composition is important. And learning the dials on your camera is critical. There's a million little dials and you have to keep changing settings, and you really have to practice doing that almost with a blind fold on you.
Yeah, again, this was Friday night, and it clouded over. We could not get any pictures of the Milky Way. Towards the end of the evening, we happened to turn literally like 180 degrees, and that's when we could see. You can kind of see Cassiopeia there. That's my one picture that I got that night of something. As I said, Thursday night, beautiful clear skies. We were not in the park. We were at the lodge. Friday night at the workshop, we're in the park, totally clouded over, except towards the end of the evening, you can see Cassiopeia.
Very
Yeah, yes. Yeah, so bad luck is not only for astrophotographers who buy new telescopes. It's pretty much for astronomers who buy new telescopes. Anybody trying to take a picture. The second night, we headed to a different site. This was not by a lake, it was a big open field. So we got there early, and the clouds started to clear, but there was still a lot of weather out there. So we decided to make lemonade out of lemons, which seemed to need to do a lot in this hobby. So this is a picture that I took. I was set up. It's kind of, I like the picture, but it's an example of not placing the tree in the right position. I do have Milky Way kind of sprouting out of the tree. It would have been nice to have it over a little bit more, but once I was set up, I was pretty committed. And if you look at these two pictures, the clouds actually add some dramatic effect, and there was a little bit of lightning on the horizon, way far off. And I was taking multiple pictures, so the first one was just really seconds before the second one, just happened to catch a bolt of lightning, which lit up the clouds. So that was a kind of neat effect. So you can see a little bit of the Milky Way there on the clouds. And as maybe many of you know, my biggest complaint about trying to do photography is focusing. So I was extremely happy that I finally got something. And this is the Milky Way from that Saturday night, and at the Howell Park Trailhead. There is a cloud towards the top. I'm going to use the, whoops, sorry. Oh, wrong way, sorry. This is the cloud here, so just so you know, it wasn't like I made a mistake with the picture. But I was excited that I was able to finally get something that evening. Okay, after we spent 2 nights taking pictures, Dan did spend some time on processing, but he was really big at stressing that you should try to come out of the field with the best picture possible. And he's not a believer in a lot of editing. The one thing he did say you probably want to do a little bit of is, whether it's Photoshop or your iPhone editing, is you might need to increase the brightness a little bit, and if you do that, increase the contrast a little bit also, so that you maintain that difference between the light and the dark areas. The other thing that you often have to do is look at your night sky. I make this mistake a lot in my astrophotography, and it's sometimes your white balance will be off in the sky. You don't see it. It's kind of either bluish or reddish color. And he suggests always checking that and make sure it looks gray or neutral. And there's a little color picker that will say what values your red, green, and blue are, and they should all be about equal. And if not, you can tweak that a little bit so your sky looks a little bit more gray background. Things like hue and saturation, he said, be very careful. His philosophy is he wants, as a photojournalist, that's his background, he wants you to look at a picture and it's something that you could see with your eyes, that you could really relate to. And I think that applies to all kinds of photography. Things like nafs and curves or nuances, but again, keep your pictures as clean as possible in the camera. After the workshop, I was able to go over to the Grand Canyon and with my husband protecting me from the moose at night. And I was able to capture, it was a little bit clearer night, these two pictures in the canyon. We were at the south rim, so if you don't see the canyon in here, because at the south rim, the Milky Way's behind you if you're facing the rim. So I just had to find some trees. These are two shots that I liked, but it was an example of composition I wish I had changed. The one on the left, I love the trees, but the Milky Way is kind of stuck on the top and there's nothing in the middle of the picture. So that's debatable. And the one on the right is a good Milky Way capture. I wish I had moved over and found something maybe a little bit more interesting. So a lot of this is taste, but little lessons to think about if you're composing in the camera.
Yes, after we left Colorado, as Donna said, we went to Arizona. Just wanted to mention one thing. I'm going to call it Murphy's Law, that on Sunday, it was a 3-day workshop, but the Sunday part of the workshop was just in the afternoon. And in the evening, Donna and her husband and I met with Stan and his wife, and we had a very lovely dinner together. That was a very nice evening. And we come back, to the lodge, and it's clear as anything. So we had Thursday night, it was clear. Friday night, we're in the park, and it's all clouded over. Saturday night, partly cloudy. We got some pictures. Sunday night, totally clear. So anyway, again, as I said, we all flew to Arizona together, but then we split up. I stayed in Flagstaff and stayed with some of you might know Barry Malthus, whose son spoke at the last monthly meeting. I stayed with Barry and his wife in Flagstaff. Donna and her husband went on to the Grand Canyon. Flagstaff is known as a dark sky city. Technically it's considered the first city designated by the International Dark Sky Association in 2001. And so in Flagstaff is the Lowell Observatory, that's the picture on the right, and also the U.S. Naval Observatory, that's on the left, and that's located west of Flagstaff. The Lowell Observatory is an astronomical research facility. Of course, many of you know it's famous for discovering Pluto, and its role in improving the universe is expanding. And the Naval Observatory, and I got to see both of them when I was there. The Naval Observatory is a dark sky site, as I said, it's west of Flagstaff, and it's for optical and near-infrared astronomy. It's also involved with research for precise celestial positioning, for our Navy ships, etc. Study star positions, etc. And this picture on the left is the 1.55 millimeter telescope. And as I said, I always had lots of problems focusing. I tried to take images of the Milky Way in Flagstaff, and I consistently did not achieve my goals. But Flagstaff is amazing. You can walk outside. I walked outside Barry's home, and right away I saw Sagittarius and Scorpio. I walked down to a park down the way, saw the Milky Way with my own eyes. It's not as bright as you would see in the pictures, but you could still see it. So I did go to the visitor center at Lowell Observatory, and I felt like I was in Nirvana, in seventh heaven, because at the top, it's a new visitor, they rebuilt the visitor center. And at the very top is this 360-degree outdoor planetarium. And so I took a picture of that, and it's a little bit hard to see, but it faces, the seats are facing south-southwest. So you see the Milky Way, you can see Sagittarius and Scorpio right there, right before your eyes. We're above a lot of the trees, and the seats are heated. So this is a great thing, as Anne, Barry's wife, said to me, she said you can put a blanket over your legs, sit there, with the cooler evenings, and they give presentations, etc. So that was just fantastic. And then we wanted to mention that Stan is having another workshop again in Colorado in September. I think it's September 10th to the 12th. I think those are the dates, or September 11th to the 13th, one of those sets of days, three days. I think it's worth it if you can get that opportunity. We had a great time, and the class is small. I think he limited it to like 10 people, and in our class there was only about 8 people, so that was really great. So, okay, thank you. Any questions?
So I just learned about this year, and we've done a project, and it's really, really cool. Okay, so next. So I'm going to tell you first a little bit about meteors, then about radio, then about how the two come together with meteor scatter mode on the radio. Then observations we did in 2025, so the first years, we had another campaign for the Geminis in December. What results we got, and then some future plans. So some terminology here on meteoroids are the bits of stone and whatnot that are in space. Meteors are shooting stars, and meteorites are the ones you found on the ground. All right. So meteors come both in sporadics and in showers. Sporadics means every day you get a couple of them, who knows from where. The showers come in whole groups of them on a certain night or two every year. They're repeatable. They're repeatable because they have been shed by some comet or occasionally an asteroid that leaves a trail of dirt behind it, and then the dirt spreads out on the whole orbit, and then eventually we run into the dirt as we pass the orbit. Okay, so in this, go back. So in this picture on the right, you see the orbit of Halley's Comet, comes from way out nearby where Pluto is, goes around the sun, comes back again. The orbits are fairly narrow, so the motion of the comet is almost always toward the sun or away from the sun. Very little sideways orbit as circular orbits like the planets have. All right, in the lower left, you see a picture of what's called the radiant. As we run into these pieces of dirt in the sky, they all seem to come from a certain place, and that's because we run into a small group of pebbles or sand, and as we look through them, we see a constellation in the background, and we see the same constellation for all of them. So one of the interesting things I think about meteors is there's the best time to observe them. It's not like the Milky Way, which is up all night pretty much, and you can go out and see it at all times. The best time to observe meteors is at dawn, local dawn, 6 o'clock in the morning. So you should start at 5 and finish at 7 and go ahead and have breakfast, and that's it. All right, so the picture on the right shows you the reason why. This is a not to scale picture. There's a picture of the Earth with a humongous person on it, and down at the bottom is a picture of the sun. That little thing supposed to be the sun. So the side toward the sun is called day, the side away from the sun is called night, and this person is in the nighttime. Now, the thing you have to know about motion in the solar system is everything goes counterclockwise. So there's the orbit around the sun is counterclockwise. The orbit around the spin of the Earth is also counterclockwise. So the person who is now sort of in the upper left there is moving counterclockwise, which is downward to the left there, toward when night ends and day begins, and so that's called dawn. And at that point, he will be at the forefront of the Earth as if it were a car running along its orbit. And there's dirt in the way, or bugs, or whatever. And you run into them, and you get bugs on the windshield, and we call them meteors. And that's all it is. Meteors, when they come into the Earth's atmosphere high up, are going at such speed, thousands of miles an hour, that they ionize the gas, the oxygen or nitrogen that they application encounter, they ionize it. Now, ionization is exactly what radios respond to. So not only do you have the ionosphere, which is the yellow region on this picture, which is caused by the sun's ultraviolet light, which ionizes the material as well. Now you have a little tiny whoop ionized patch caused by this meteor going through. The ionization spreads out and disappears in a few seconds. But for a while, it's brilliantly shiny, whereas the bottom of the ionosphere in general is kind of wishy-washy, dirty mirror looking. And now you have a shiny mirror in the sky at just about the same altitude. Here's a diagram for how you would calculate the effect of a particular meteor trail on the Earth. And I want to point out that it's got all sorts of angles. Moving on. You can also calculate from that different things about the expected reflection of a radio wave from such a small, narrow ionized trail. So the lower left is the strength of the scattered signal, sorry about spelling, and the one on the right is the duration or length of time you would be able to see it before the trail would disappear. So the interesting thing for the first one is that it's dependent on lambda cubed 3 times, and the one on the right is dependent on lambda only squared. So if you had 2 different lambdas, 2 different wavelengths of radio, you could see a difference. This is the prediction. Well, we have tiles on our radios and we can make that happen. Thanks. So here's one of those the formulas just plotted up. The strength depends on the radio wavelength cubed, but the strength or power that you receive from your radio is difficult to measure because each ham operator has a different kind of a radio, or a different antenna, or a different placement of these, higher trees or not. And we're going to do an experiment with lots and lots of different people. We're hoping that statistical averaging will save the day. So far, this has not happened. Duration depends on wavelength squared, and duration is time. Time we can measure. This is going to be our salvation, this one. The time will eventually tell us the mass of each of these little particles. And that will be something new for the science. So we have 2 bands that are particularly good for this sort of scattering, the 6-meter band and the 10-meter band. And it is only this last year that the 10-meter band has been opened by the FCC to being used in high-speed communications, which is what we're going to do here is high-speed communications. So to go from the 6-meter band to the 10-meter band on the radio, the strength should increase by 5 times, and the duration should increase by 3 times. We can do an experiment here, right? Next. So here's one of the people to do the experiment. The whole high-frequency band is from 3 to 30 megahertz. We have 700,000 ham radio operators in North America. This is way more than the number of amateur astronomers. There are millions of operators in the world. You have to take a test and a licensing procedure to be allowed to broadcast. So it's people who actually know something. The ionosphere is from 100 to 300 kilometers altitude. The meteors are from like 100 to 150 kilometers where they decay. It's going to be an interesting thing. So this is the sort of setup you have. Next. Here's all cleaned up. You have a radio, you have a power supply, you have a computer. You got to run some special software, which is the interesting thing here. These scatterings are bright, but very short duration, sort of like 2-3 seconds you have. I think what use is that of any sort? But the Canadian mining corporations have been using this for 100 years. In Canada, there's a lot of auroral activity, and the aurora messes up the ionization in the ionosphere. And if you are trying to transmit by bouncing the radio signals the ionosphere and then back down around the curvature of the Earth to somebody else, and there's an aurora in there, it makes it very garbled and just difficult to understand. But if you have a nice straight piece from a meteor trail, it's crystal clear. But it's very short. How much do you say in 2 seconds, right? So the Canadian mining corporations in the high Arctic wanted to communicate with their banks, which are right across the border from New York State. And it was required that they would report every day how much they had mined the previous day. They had no cell towers. The satellites are messed up because that signal comes through the ionosphere twice. So this is very difficult to communicate, but they found the meteor scatter was sharp and clear. Now, if you have something that's very short, though, what you do is you write type out in Morse code your message, you put it together really, really fast, and you repeat it multiple times a second for 15 seconds, and you stop and you do it again. If you do this for a whole hour, then there are enough meteor scatters that pieces of it come through, and it's crystal clear and can be put together. So they've been doing that. That's what they communicate with. So I think that's just really interesting. It's all now by software-defined radios. I want to call your attention to the first line. It's using the software called WSJTX and MSK144 you have to set it to is one of the subparts. I call your attention to the JT. The JT is Joe Taylor. He's the one that wrote the code originally for this, and in fact is still tweaking. Joe Taylor has a Nobel Prize in Physics for binary pulsars. And, but he's a ham and he loves this. So we're so happy that Joe wrote this software. Okay, next. The type of signals that you see, we call them pings. Listening on the earphones, you hear this noise, ping. I don't think it sounds like ping, I think it sounds like shush. There it is. And those are some sort of transmission between you and somebody else by means of this little tiny shiny spot in the sky. So meteors can be either underdense or overdense. Underdense means they're very small. Overdense means they're a little bit bigger, like a grain of sand. And the underdense ones have a sharp fin type of response. So it has a sharp rise and then an exponential decay. So like that. And it is the exponential decay in time which will tell us the mass of the particle. So in the upper right, you see what a underdense, what looks like it's just a sort of sharp signal there. Is that weight thing there? Okay. The overdense ones make a block, so that's the one down by here by the red arrow. It goes up, wobbles around, well, comes back down. And the bottom one, this picket fence one, is what you see from an airplane going by. Next. We use wave files, an audio file. What you hear, you can get your sound card to record this, and that becomes very crucial in doing the scientific analysis. So we have to get all these people to take wave files and then send them off to Zenodo, and then we get them there. We want to measure the duration of each of the underdense signals in particular. Science results. We want to test some of the assertions from McKinley's book in 1961. We're going to determine the effects of the ceiling height, how far up the meteor was, and we want to eventually find the communications footprint for meteor scatter. So a whole bunch of people in New Jersey could see the same meteor, and the people in Pennsylvania may not see it at all. So that sort of geographical spread. Okay. So in 2025, we had 2 QSO parties. That's a observation with your radio party. In the first one, we had 75 people take part. And then for the Geminis, we had 55 people take part. So I think it's interesting, each of these people recorded for several hours, so 5 o'clock till 7 o'clock in the morning, and got thousands of pings each. So we were surprised at how many pings there were. So this required that the student learn how to do AI to have sorted out. She chose random forest as the machine learning thing to use, and managed to get it to determine from all these wave files what was a meteor and what was a non-meteor signal. And from the trading set came out that the machine finally was good. Got 85% of them accurate. Well, okay, that's pretty good. And mostly were underdense meteor signals, and 88% were underdense for the Perseids and 79% for the Geminids. The previous number had been 90%. These are close to 90%. But we're wondering if next year, this year, we're going to do many more of these campaigns, if maybe the number, the 88% or the 79%, is different for each shower, and maybe there's some showers that have a bigger number so that can pull the average up to 90%. We don't know. In both showers, the percent of overdense ones did increase for 10-meter band, and so that did support McKinley's view on that one. Did the 10-meter band also have more power? We don't really know yet. That's a difficult one to do, and we have not measured the duration spectrum yet. But citizen science works, and we had, about 100 people finally to do this. It was really great. Hopefully more this next year. So future plans, we're going to do more meteor shower QSO parties. We had one already on May 6th, and going to do for the others. We want to get more ham operators interested in this rather peculiar sidelight of their hobby. We're going to try more frequencies, not just the 2 we've used. And then we compare them with radar and optical observations. So in optical observations, some showers are short, some showers are long, 2 days, 3 days, see if we can pick that up, and then try to analyze the power and the duration of it. And we want to do it for more years. Okay, so we've been interested in planetary nebulae and in several varieties of investigations of them.
So, as Dr. West said, we're interested in a bunch of different planetary nebulae because they're super cool. They have these bright colors. Many of them are easy to photograph, and they're just these crazy kind of shapes, crazy kind of images. And a lot of people here at AI have taken cool pictures. There's the Ring Nebula by Clif Ashcraft and the Helix by Sharfman. And so we wanted to know a little bit about the shape and about the center of those planetary nebulae. These are some more images. That's the Dumbbell Nebula and the Little Dumbbell. I like to think the Little Dumbbell kind of looks like an apple core. And yeah, I mean, they're super cool. And something that always blows my mind is you're looking at them from one perspective, but they've got a 3D shape. It's like there's more going on around it that you don't even see. So the first step in our little experiment was analyzing the shape. And we did that by taking images that different members had taken, and we printed them out, and we used little thumbtacks and strings to draw ellipses around each nebula. And then for each one, we drew the major axis and the minor axis in the center and measured different radii, 8 different radii every 45 degrees to the edge of that ellipse. And what we did is we kind of compared for different planetary nebula that difference in the radii and the circularity, how close the radii were to each other, kind of how circular it was. That also meant noting different shells, rings, layers, and just kind of plumes that just like stick off. We would calculate the axis ratios of like the minor axis to the major axis, and the eccentricity, which is a measure of its like squishiness almost of the ellipses. Then we used SIMBAT to log different information, other information about Auer's nebulae, and Auer was the inspiration paper that we kind of took and explored throughout our project. We used the Planetary Nebula Image Catalog from the University of Washington to get some other pictures of those 38 that we maybe didn't have taken by a member, and we used the Hubble Space Telescope as well. So that's kind of what our measuring of the shape look like. That's the Blue Snowball Nebula. As you can see, it's much more circular, so all those radii are pretty similar, whereas this one, I forget which one this was, is much more elliptical.
It's not showing up, just go on.
You can't see it. But yeah, so we took pencil, traced down the shape, kind of drew the lines out. And then what is a planetary nebula?
My turn. Thank you. Yeah. So the reason that planetary nebulae are interesting, besides being beautiful, is that this is the end of a sun-like star's life. That's 0.88 solar masses. And there are 3,000 of them in the catalog of the Milky Way. Only 1% of them have known binary central stars. Binaries are generally 30 to 70, sort of 50% of field stars are binaries. And it is often thought that binaries are the cause of some of the odd shapes of the planetaries. So then the question arises, are binaries truly rare in planetary nebulae, or they're just hard to identify? They're can't tell. And do binaries indeed cause the pointy non-circular shapes of these things? If we could understand some of these things quantitatively, then our goal is to understand mass loss as the star is puffing out its outer layers, and thereby stellar evolution. So hot topics in astrophysics. So we have this paper by Aller and et al. About planetary nebulae seen with TESS. So TESS is a satellite. It's not meant for this at all. It's meant for exoplanets looking for transits. However, it's taken lots of pictures of lots of star fields all the time, and by gum, these other things are in the pictures as well. So their paper was published in 2024 in Astronomy and Astrophysics, and they were looking for variability in the central stars of planetary nebulae, with the idea that if the variability were periodic, say that they're binary stars in there, and try to find more of them. So they looked at 38 central stars in planetary nebulae, 2 of which had been imaged by AAI members, so we measured their pictures, right? Our pictures, not their pictures. In their study, they found 8 known binaries in the group, and 18 were candidates. So that was a big number, 18 is bigger than 8. And you add the 2 together, you get 26. So 26 out of the 38 they studied, which is 68%, are possible binaries. And that's similar to the field star number as well.
January 2026, astronomer Roger Resnick and his team discovered a mysterious large iron structure, a bar within the Rig Nebula M57. That's this red bar going across the long diameter of the Rig Nebula, going right through where the white dwarf in the middle is. us have looked at the Rig Nebula or taken pictures of it many times, and none of us have ever seen this thing. And they never saw it with the Hubble Space Telescope either. And the reason is that this was a thin cloud of ionized iron. A light year distant Mars mass cloud of iron atoms in a previously unknown bar shape, potentially representing a vaporized planet. So there may have been a planetary system around that star that developed into the Rig Nebula. The instrument they used was the Weave instrument, Enhanced Variable Velocity Explorer of the William Herschel Telescope. The structure is a long, thin cloud of ionized iron atoms found in the center, and it extends for about 500 times the distance of Pluto's orbit from the Sun. The estimated amount of iron in that central bar is comparable to the mass of Mars. You can imagine it might even be the mass of the Earth's iron core, which is about the same amount. This bar was not detected in decades of previous imaging, even by Hubble and the James Webb Space Telescope, because it's only visible through specific spectroscopic vacuum of iron emission lines. You can see that this is the spectrum of the Rig Nebula, and there's a couple of bands in the short wavelength region of the spectrum, which were isolated by spectroscopy and enabled them to detect this thing in imaging. Future observations are needed to determine why the iron took the shape of the bar and if other elements were present. These findings were published in the monthly notices of the Royal Astronomical Society. One thing I noticed about this situation is that we have some really good narrowband imagers in this club, and narrowband filters are available. If you look at the, excuse me a minute, look at the shortwave end of the spectrum here. This purple area is the bandpass of a filter that you can buy from Edwards Scientific. When we decided to get one, Barry Lou ordered one and bought it, and Tony Sharfman did a 3D printed holder for it, and I thought it would be a good idea to see if we can image this thing too.
Okay, so like Cliff said, I got this filter. It was not designed for astronomy at all. I suppose it was made for spectroscopes. It's a weird size. So I had to adopt it to my setup. And our question was basically, can we find anything like that in other planetary nebula? So unfortunately, M57 is a summer object. I can't image it yet, but I was going to try it when it was visible right now. So this is M97, the Owl Nebula. And at first, I got absolutely nothing. In 10-minute exposures with this filter, it's just pitch black. So I kept throwing more and more time at this thing. I think it was like 5 days, and 32 hours. And you can kind of, it's a very grainy image here. You can kind of see some structure starts to come out. On the right is hydrogen alpha oxygen 3 image of the same thing that I did some years ago. You can see that there's roughly the same structure. My guess is that we're not actually seeing iron because this is so faint. This is probably the same gas emitting in that range. Mary Lou probably knows better than I can. But it's inconclusive. So the goal is to image more of these. See if nobody has this filter yet, nobody's playing with this. Maybe we can find something before anybody else does. Just for the hell of it, I tried M27, which is just coming out very late, like 2 a.m., 3 a.m., I think it was. This is much brighter than M97, but you can see the core of this. This is not a lot of exposure time. I think it's half an hour. Basically resembles what you see in the other two as well. So I don't think this is iron either. Again, inconclusive. But since I already had everything set up, I decided to just do some experiments and shoot galaxies. So you can see M101 on the left, M51 on the right. And this violet filter definitely brings out structure. You can see that pretty well. This is not, well, they're very dim compared to visible light. But what I found interesting is this filter is not affected by light pollution at all. There are no gradients in these images. They're absolutely flat. That means that whatever illumination we have in our cities, there's no violet at all. There's probably blue. There's plenty of orange and stuff, but there's no violet. So I got pretty excited for a minute there. I was like, hey, can we use this to kill light pollution? Unfortunately, it also removes a lot of the light from the galaxy as well. So you could use it, but you would have to take hours and hours of images anyway.
So this, I think, is really exciting. The detail you see on the galaxies in the violet filter is really exquisite. And maybe this will be the fun thing to do. I don't know. So results in future work. This whole project is in its initial exploratory phase. We have no results to report. We plan to measure more images of planetary nebulae in the violet filter. We will look for more binaries in the literature, see what we can find about that. Measure more about the properties and the shapes in a better way to do it. We especially want to see the ring nebula where it comes up. If we can, with this small filter, duplicate what the people did in January